All right, everyone. Um, while you guys settle down, maybe just a couple of administrative things. So I'm sure you're all aware this Friday, basically day after tomorrow, we'll have quiz two. I sent out an announcement about that quiz. It includes everything up until Castigliano's second theorem for trusses. Okay, the beam and frames is not included. Um, I think, yeah, but Dr. Liu did a couple of examples last time. So maybe before I begin, I can talk a little bit about that. Koi, were you able to complete this example? No? Did you guys begin this? Okay. So I'll just very quickly kind of lay out the outline of the solution, and then I'm sure you can go through the details of the calculation and make sure it makes sense. So in this problem, what was asked was, well, first of all, it's a two-segment beam. A part of it is fixed at A, and there's a internal hinge at B, and a pin joint at D. And the problem says find the vertical deflection at B and slope to the left and to the right of the hinge. Okay, so for this problem, basically the first thing, like any other Castigliano's method problem, what you would do is solve the actual system, the actual structure with the actual loads, and I'll let you verify that this should be the bending moment diagram. Clearly, moment here should be 0. And so essentially what happens is that the right segment acts as a simply supported beam and the left segment acts as a cantilever beam. So that's the actual loads. And then to calculate the vertical deflection at B, we apply an additional load Pi at that point. And under the action of that Pi, we get, well, of course, this guy will just move down as it is without any moment. And there'll be a bending moment similar to a cantilever beam with a tip load for this. And applying the other part of the Castigliano's theorem, second theorem, that's important is taking the derivatives of the internal bending moment, and if you have a shear or an axial or a torsion, you have to take derivative of all those things as well. So derivative of the bending moment diagram due to the additional load with respect to Pi, not with respect to x, gives you just x1. So that x1 goes here, derivative times curvature, right? Additional derivative times real or actual curvature is what we need. This actual curvature was 41x squared minus x1 squared. This is basically just the equation of this bending moment diagram. And at that point, you have all you need to do is to evaluate the integral. I'm sure you can go through and follow the equations. The most important point, of course, is setting up the correct integral, for which the most important thing is to calculate the additional derivative and the actual curvature. Okay. Um, and for the other parts, when it's asked for you to find slope to the left and slope to the right, really there's just two separate problems. You need to find slope to the left, and if you want to find slope to the left, you need to apply an additional moment to the left of the hinge. If you want to find slope to the right, you need to apply additional moment to the right of the hinge. Okay. So if you apply an additional moment to the left of the hinge, you should be able to see that this segment comes into a constant moment, mi, and the right hand side there is no moment, right? If I take the derivative of that constant moment, I get 1. So similarly, I take 1 times the actual curvature. To find theta b on the left side, I take the derivative times the actual curvature, and rest of this as just algebra. And similarly for the right hand side, now the bending moment diagram is a little more interesting. On the right hand side, I'm applying a moment mi, additional moment mi. But on the left hand side, there is no moment because there is an internal hinge. So this moment will cause BCD to behave like a simply supported beam with an end moment at one point, right? So BCD would be behaving like a simply supported beam with an end moment, and we know that the diagram would look like that for such a beam. And AB would behave just like a cantilever beam with a tip load of Mi over 8. So the bending moment diagram kind of looks like this. And the jump, of course, is due to the additional applied moment and the fact that there is an internal hinge. So once that bending moment diagram is in place, all you need to do is to take derivatives of that bending moment diagram. You get Mi over 8 here, Mi over 8 here, and just take the two integrals. Uh, Note, I think that one of them is integrated from the left and one of them is integrated from the right. Um, and the rest is basically just calculations. Okay. Um, so for Castigliano's theorem, again, the procedure and the concepts are very different from the virtual work method. But at the end of the day, the calculations end up being exactly the same as the virtual work. So if I ask you to do something by Castigliano's second theorem, you need to actually apply an additional load, not a virtual load. You apply an additional load and take derivative with that, and then show what integral you get. Okay. Any particular questions about any of these, either any of these parts of this problem? I'll post this handout, and I think, oops, let's see, is this working? Uh, I'll post this handout, and I don't think Dr. Liu's video lecture got recorded very well, so that won't be posted, but of course, all of this is being recorded, so you can take a look at it later on. Okay, no questions? All right. Okay, so we'll switch gears and we'll jump into a topic, if this will allow me to change the window here. Let's see. All right, so we'll switch topics, and looks like my digital pen is not working today. Let me try something. Okay. All right, there we go. So, so the topic that we're going to look at now is basically analysis of indeterminate structures using the force method. And to some extent, I think you've already done some of these types of problems, maybe simpler problems back in 371. So the idea really is that um, you know, for indeterminate structures, equilibrium alone is not enough, right? If I have a structure that is determinate, you can find all the reactions, all the internal forces, everything, only using equilibrium, by using equilibrium itself. But if a structure is indeterminate, then all the internal forces, the reactions, and everything else will depend upon not only equilibrium, but what else? Compatibility or continuity, and how stiff the material of the structure is. So, for example, I guess I'll give you more examples. So, if I have a simple cantilever beam like this, and I apply a tip load, it's a determinate structure. You can find bending moment diagram and shear force diagram, everything, all the internal forces, calculate deflections if you want, anywhere in the beam, right? It's all determinate, no trouble. The deflections, of course, depend upon the material properties of the beam. But if, say, I have an additional support in the middle, and then I apply a tip load to the cantilever, that immediately becomes an indeterminate system, right? And in that case, the reaction at this point would depend upon the material properties of the beam itself. So anytime you have an indeterminate structure, equilibrium alone is not enough. You need to have compatibility. Compatibility you need to have in any case always, but it's the material behavior that allows you to find the internal forces. Maybe another simple example. If I have, say, two springs, okay, I attach two springs to the ceiling, and I attach a plate to both the springs. The plate is being hung by two springs from the ceiling, okay? Assuming that the plate does not kind of wobble like this, it goes up and down uniformly. The displacement in the two springs would be exactly the same. But would they be carrying the same force? Would the two springs be carrying the same force if I am attaching the plate to the two springs? That's right, it does depend upon the material of the individual springs. If both the springs have the same material, exactly similar height, similar stiffness, then yes. If the total load of the plate is P, then P over 2 and P over 2 would be carried by each of those springs. But say one of the springs is extremely soft, right, and the other spring is much more stiff, then where would the load go? To the stiffer spring, right? Even though the displacement for both of them would be exactly the same, the softer spring does not carry any load because the displacement is very small. The stiffer spring, even with a small displacement, carries up most of the load of the P. So that's an example of a system that is indeterminate. Simple two springs hanging from the ceiling. You cannot use equilibrium to find the forces in the springs. You cannot use equilibrium alone to find forces in the spring. We need material properties of the two springs. Okay. So that's in general true for indeterminate structures, and they are of course characterized by how we understand the number of unknown forces, reactions, or unknowns in general is greater than the number of equilibrium equations we have. If that's true, it's an indeterminate system, right? We've seen those types of indeterminate systems lots of times. Now, in practical life, a lot of the structures that we come across are actually indeterminate. And it's made so because when you have indeterminate systems, it gives you a little degree of redundancy, so that if one of the components fails, your structure doesn't come crashing down, right? Also, indeterminate structures have smaller deflections in general, and they have more stability. But the biggest advantage of having an indeterminate structure is redundancy for load paths. If if one of the members fails, you still have other alternate load paths. Disadvantages, of course, you need more material because, of course, it's an indeterminate system. More material means more cost, complex connections. And the other key characteristic idea of the indeterminate systems is that there can be initial or residual stress or misfit stresses in an indeterminate system. So let me go back to the very simple example of those two springs hanging from the ceiling. Okay. Now, if I attach a plate to those two springs and keep the plate exactly horizontal, what happens if both the springs are not exactly of the same length? Maybe one is slightly longer, one is slightly shorter. Under this plate hanging from those two springs, what happens if the two springs are not exactly the same height or not exactly the same length? The shorter one is going to have initial stress, and the longer one would have initial stress, right? So shorter one and the longer one, the shorter one would have to be extended a little bit to match with the longer one. The longer one would have to be compressed a little bit to match with the shorter one. So for indeterminate structures, even when there is no load, there can be initial stresses, and then you attach the plate to those springs. Okay, so that would not happen in a determinate structure. If it's a determinate structure, there's no initial stresses. Without any load, there's no stresses. Okay. Now, how do we analyze them? It's the same sort of thing. we use the same four conditions: equilibrium, compatibility, material behavior, strain displacement relationships, and boundary conditions and loads and everything given in the problem. Let me quickly ask you this. This is a frame, a three-story frame, three-bay, three-story frame. What is this indeterminate or determinate? I'm applying gravity loads, some lateral loads. Is this frame determinate or indeterminate? Indeterminate, highly indeterminate. But to what degree of indeterminacy is this frame? What is the degree of indeterminacy of the frame? Any ideas? How can we determine degree of indeterminacy of this frame? Miles?
How many more reactions have
Right, so reactions, definitely you have three here. So at all the four supports, you have three reactions. So that immediately is 4 times 3, 12 external reactions, right? 12 external reactions, and how many equations of equilibrium would you have? 3. So there is a degree of indeterminacy of 12 minus 3, 9 in 9 degree of indeterminacy external. Okay. So even if you were to be able to calculate all the external reactions, would you be able to calculate all the internal shear force bending moment diagrams and everything? Not yet. Because let's say if I give you the reactions, XY forces and the moment at all of these fixed supports, even then, if I ask you what is the bending moment somewhere internally in the hinge in a column or a beam, you would not be able to do that just by using equilibrium. You would have to continue to solve it. In fact, one way to think about indeterminate structures is that if I were to take a vertical cut right here, and a vertical cut right here, and a vertical cut right here. So kind of like there are these four sets of columns, and I'm cutting them, making them all independent. Okay. So all of those independent structures, if I look at this structure by itself, now it's very similar to a cantilever beam or cantilever column, which is determinate, right? So when I make a cut through this beam, how many new unknowns have I introduced? 3, right? Yeah, because X component, Y component force, and internal bending moment, those would be the new unknowns I've created. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is the total number of cuts that I'm making, times 3 unknowns, 27 total unknowns we have. How many equations do we have? Excuse me. So we'd have one structure, 2, 3, 4. 4 independent structures if I make those 9 cuts. 4 structures times 3 equations each, right? X, sum of forces in the X, sum of forces in the Y, and sum of moments. So 4 times 3, 12 would be the number of equations I would have in all. And there are 27 total unknowns. So 15 is the total degree of indeterminacy of this structure. Even a simple sort of a simple looking structure, 3-bay, 3-story frame is highly indeterminate. And of course, in real life, structures are much more, have a much higher degree of indeterminacy. So now how do we solve such structures? Till now, we've been looking mostly at determinate structures, which is all good and fine. But real life, of course, most of the structures are indeterminate. So there's primarily these two methods that I've outlined here. One is a force-based method, also called a flexibility method, and the other is a displacement method. The concepts behind these two methods are, of course, different. One of the methods, the force method that we'll begin today, is based upon the idea that any indeterminate structure can be converted to a determinate structure with some additional redundant reactions or forces. So for example, the example that I was giving you was that cantilever beam with a center support out here, right, with a tip load. So I can imagine this structure to be a superposition of a cantilever beam without the support with a real applied load here, and of a cantilever beam with a load applied in the middle. And that load in the middle would have to be such that the displacement that I get, the total displacement I get due to the actual loads and due to the redundant reactions is zero. So that's the idea behind this force method. And essentially what we are doing is we are converting the indeterminate structure to an underlying determinate structure. We apply superposition and compatibility, basically saying that deflection or displacement of the support should be zero. And we solve for the unknown redundant forces in this case. So this is for force method, the unknown redundant forces are the unknowns that we are solving for. And what we need are flexibility coefficients. We'll go through that. And of course, at the end of the day, if you do all of that, usually you end up getting a system of equations to solve. So here, if you have a system of equations to solve, hopefully you've all solved simultaneous linear systems of equations. You can express that in the matrix form, where A is the flexibility coefficients, X is the unknown forces, and B is the known displacements of the determinate structure. And we'll go through all this, so don't need to jot it all down. Just before I begin the force method, I'll also sort of tell you how this contrasts with the displacement method. In the displacement method, the idea is that we can take any structure and we can break it up into all of its individual parts. So for example, if I have a huge truss which is very highly connected, that makes so almost all of the nodes are connected with each other, then there are lots and lots of internal members in that truss, right? Which makes it very highly indeterminate. So if you take that big truss, highly interconnected truss, and imagine each one of those members individually, then you can actually describe what happens to each member very well. If I apply a force F, it will have a displacement of PL or FL over AE. We know that force displacement relationship for each individual member, right? And the trick there is that if I assemble all of these individual force displacement relationships together for the entire structure, then I would be able to solve for the unknown displacements at the nodes. So here, what we use is we express the local force displacement member relationships for each one of those members. We assemble them and use equilibrium to solve for the unknowns, which are usually displacements. And at the end of the day, we again get a system of equations to solve. So no matter which method you use, at the end of the day, you're going to be solving a linear system of equations. And actually, this statement is much more general. Almost in any field of engineering, you boil down a complicated set of differential equations down to something like this, a system of linear equations that you can send to a computer and let the computer crunch out the numbers. Because that's what computers are good for, solving big, huge linear or nonlinear systems of equations. Okay, so here the stiffness, like AE over L, I mentioned that stiffness is this matrix here. D is the displacement unknowns in the entire structure, and F are the external forces. So stiffness method we'll do a little later in the course. Right now we'll focus on this force method. But both of these methods are very effective for solving indeterminate structures, right? So here's a very simple example. I was talking maybe a little bit differently of this example. Cantilever beam with an end roller support and a load in the middle. What's the degree of indeterminacy? What's the degree of indeterminacy? That's right, 1, right? So if I remove this support, it's a cantilever beam with a load somewhere in the middle. A cantilever beam is determinate. If I add this support, then I'm adding one more redundant force to the structure that cannot be solved with equilibrium alone. So the way we'll solve it is we'll imagine this structure to be a superposition of two structures. One cantilever beam with that load, no support, and another cantilever beam with a redundant unknown force up until now. I don't know what that force is, but I'll calculate it. And the idea is that under the actual load, the beam will deflect kind of like this, have some displacement due to actual loads. And due to the unknown redundant force, it will have a displacement like that. If I add them together, then the result should be 0. And that's basically what compatibility is. So that would be an equation of compatibility that you would have to write for other problems. In this case, it's quite simple. In general, it's usually quite simple, but not this simple always. So how do I calculate this by? The logic that we are going to use is that if I were to apply a unit load here, then I know what that displacement is. Okay. And I'm going to call that displacement under a unit load FBB, meaning flexibility for displacement at B with a unit load also applied at B. That's why there are two B's. So maybe I'll write that here. The first B denotes that we are measuring the flexibility of displacement at B. And the second B says that there is a unit load at B as well. So this flexibility is essentially the if I apply a unit load at the tip, what is the displacement at that point? Other points have different displacements. So I could be measuring flexibility, say at some point C, midpoint of the beam. That flexibility would be FCB. Okay, so what we are talking about here is flexibility of the displacement at point B for a unit load applied at point B. And this is a notation that's important. So we'll make sure that as we go forward, I'll do that quite a bit. So if I know the displacement for a unit load, displacement for a load of By would be what? Displacement for a load of By would be Joe? Go ahead. It's not that complicated. If I apply a unit load, I get a displacement FBB. If I apply a load By, what do I get? What displacement do I get? FBB times By, right? So this would be equal to simply FBB times By. And then I can substitute that into the compatibility equation. I get delta B minus FBB, and I'll write that in the matrix form, times By equal to 0. Okay, so essentially you'd be solving the system of equations that FBB times By, which is the unknown, is equal to delta B, and which is the same system of equations that I was telling you on the previous page. Ax is equal to B, except that there is not really a system of equations. There's just one unknown to be solved. So the key things here to note is that this delta B under the actual load, I know that. I can calculate that, right? We've been doing all of that with our virtual work method and with any method that you want. This FBB is also something that the flexibility is something that I can easily calculate. The only unknown in this equation is the unknown redundant force By. So if I know delta B, if I know FBB, I can easily calculate By, right? That's the force method course, a very simple depiction for a simple problem. It gets a little more complicated for structures which have multiple degrees of indeterminacy. For example, here, A, B, C, D, there are 4 supports for a continuous beam. What's the degree of indeterminacy for this? 2. Why is that? Because if I take out any 2 of the supports, maybe I take out these 2 supports. Let's see if I can capture them. If I take out these 2 supports, now it becomes a simply supported beam with an overhang, determinate. Or, as I've shown here, if I take out the center 2 supports, then it becomes a simply supported beam, of course, which is determinate. So the idea here would be to take this indeterminate structure and to express it that this structure is equal to a determinate structure with the actual loads plus the same determinate structure with one redundant unknown and plus the same determinate structure with the other redundant unknown. So if your degree of indeterminacy increases, then then the number of analyses that you would have to do also keeps on increasing, right? So in this case, since the degree of indeterminacy was 2, I would have 3 structures to superimpose: the actual, redundant force 1, redundant force 2. If degree of indeterminacy was 10, you would have to do how many analyses? 11, right? 1 for actual loads and the determinate structure, and 10 redundant forces. So you can see that this gets complicated fairly quickly. But let's see what would be the compatibility equations in this case. The first step would be that we want to make sure that the displacements at B and C are 0. For this determinate structure, there of course there won't be 0, but we can calculate delta B and delta C. Can we calculate delta B and delta C for this determinate structure? Or can you calculate delta B, delta C? If I gave you simply supported beam with a couple of loads P1 and P2, and I ask you to calculate displacement at this point and this point, something you can calculate easily, right? So these 2 displacements, known displacements of the underlying determinate structure can be calculated. Similarly, this guy would also deflect, and the last third structure would also deflect. We would have to calculate the deflection of the second and the third analyses also at the points B and C. So I'm going to write that as this displacement and displacement at B and displacement at C. What should I call this displacement? Okay, delta B prime. But in what would that be equal to? It would be equal to FBB times BY. Why is that? Because if I were to apply a unit load at this point, I would be able to calculate the displacement at this point. That would be FBB. And if I multiply that with BY, I get the displacement at that point, right? Similarly, if I take delta C prime, let me make sure that I'm using the consistent notation here. So let me call this delta B B prime because it's the displacement at B due to an unknown redundant force at B, which is equal to the displacement at B due to a unit load at B times By, and this guy will say is delta CB, which is FCB times By. What is FCB? That C means displacement at C, and the second B means unit load at B. So when I use these two subscripts, the first subscript denotes the point at which we are measuring the displacement, and the second subscript denotes the point at which the load is applied. Similarly, for this guy, when I apply a load at C, I measure the displacement at C. I'm going to call that delta C prime, which would be equal to FCC, the displacement at C for a unit load at C, times the unknown load Cy. And I'm going to also measure the displacement at point B due to this, which would be delta what? BC prime, displacement at B due to a load at C, which would be equal to FBC times Cy, right? So all I've done till now, I've broken up the structure, the indeterminate structure, into sequence of 3 determinate problems. And what I want to do is I wrote out what the displacement at each one of those 2 points, B and C, would be under all these different loading cases. Now, what should the compatibility equation say? What equation of compatibilities do I need? Right, so all that those two compatibility equations should say is that under the effect of these 3 cases, the total displacement at B should be 0 and the total displacement at C should be 0. Right? All that this should say really is that delta B should be 0. I shouldn't say delta B because delta B is this is just this. So the total displacement at point B would be the sum of this delta B plus delta BB prime plus delta BC prime. Make sense? So I'll write that as delta B plus FBB times BY plus FBC times CY. That total displacement has to be 0. That's compatibility equation 1. Similarly, delta C plus FCB times BY plus FCC times CY equal to 0. Those are the two flexibility. Those are the two compatibility equations. Question? Okay.
I thought it should be minus.
Minus? You're right. It should indeed be minus. Actually, no, because what will happen in the end is that the value of By and Cy will come out negative. So just saying that actually By and Cy should be pointing upwards, not downwards, the way I have drawn it. Okay. So the sign of that term in the previous case was negative because I had applied By up, pointing up in the previous case. Right now I'm applying By pointing down. So the idea is that the total displacement under the action of all of these forces should be 0 at point B and at point C. Now, one thing that I would point out here is that a convenient way to write this equation is in the form of a matrix. So the only unknowns here are By and Cy. I'm going to circle the unknowns. Everything else is known. And no matter how high your degree of indeterminacy is, you can always do this. You can write compatibility equations for each one of those redundancies, right? And in that case, you can write your unknowns By and Cy as a vector, and you can write your flexibilities FBB, FBC, FCB, and FCC. It's a 2 cross 2 matrix multiplying a 2 cross 1 vector. So hopefully you can see that FBB times BY plus FBC times CY is those two terms, and it should equal to minus delta B and minus delta C. right? So all I've done here is taken those two equations up there and converted them to a matrix equation. Once it's in the form of a matrix, then it's very easy to solve. Just send it to a computer, it'll crunch out the numbers. Doesn't matter whether it's 2 cross 2 matrix or 100 cross 100 or million cross million, right? And believe me, there are structures and problems where you're solving really million cross million equations, system of equations. But anyway, so this is the idea behind solving multi-degree of indeterminacy. But you might think that, to calculate each one of these flexibilities, we are really going to have to apply a load by, calculate the displacement at here, calculate the displacement here. Similarly, apply load at C, calculate displacement at these two. And if there were really a million degrees of indeterminacy, then you would have to apply a load at each point, measure the displacement at a million other points, which would be very cumbersome. So let me not go to million points. Let's make it 10 points. If there were 10 points, you would have 10 different structures for which you would be measuring displacement at 10 different locations, right? 10 times 10, there would be 100 analyses that you would have to do, because the size of that matrix would be 10 cross 10, right? And if I have to calculate each one of those entries, then 10 cross 10, there's 100 entries to calculate. But something helps us in this case. The theorem of reciprocity helps us quite a bit in this case, because what happens is, it turns out that this matrix, this flexibility matrix, turns out to be symmetric. That the displacement at B due to a unit load at C is the same as the displacement at C due to a unit load at B. And the reason for that is this Maxwell theorem. So let's take a look at how you would calculate actually displacement at B due to a unit load at C. That's this problem, right? So think of this Cy as a virtual load, and if I were to find Cy or apply Cy as a virtual load, and to find the displacement at B, sorry, to find the displacement at B due to an actual load Cy, we would apply the virtual work method, and uh, we would calculate the moment M due to a virtual load at B, and curvature due to a load at C, so M over EI, and integrate that from 0 to L and dx. Does this make sense? What I've written here, that I want to find the displacement at B due to a load at C, a unit load at C, right? So this FBC is finding the displacement at B due to a unit load at C. I find the response or the bending moment along the beam due to a virtual load at B, and multiply it with the real curvature due to C. That's why I wrote that in red and this in blue. Okay, this is just applying virtual work method. So hopefully you can convince yourself that this is true. And on the other hand, if I write FCB, then I'm measuring the displacement at C. I'm measuring displacement at C due to the real load at B. To calculate the displacement at C, I would apply a virtual load at C, find the bending moment diagram due to this virtual load at C. I'm going to call that MC, and going to multiply that bending moment diagram due to a virtual load at C with a real curvature due to bending moment because of the load B, and that would be MB over EI. And of course, I integrate that from 0 to L dx, and clearly these two expressions are exactly the same. Mathematics doesn't know color, so these two expressions are exactly the same, right? So, which means that FBC is equal to FCB, and that is a fundamental, relationship that allows us to say that this coefficient matrix, flexibility matrix, would be symmetric. So I don't need to calculate 100 unknowns. I only need to calculate the symmetric half of that. What would be symmetric half of 100 unknowns? Close to 50, but not exactly 50, right? So it would be basically, if you think of it as a uh, triangular set of flexibility coefficients that you're calculating, you'd be calculating one unknown in the first line, two coefficients in the second, and 3 and 4 and up until 10. So 1 plus 2 plus 3 all the way up until 10. How much would that be? 55, right? Because if you don't remember that formula is n times n plus 1 divided by 2. That's the number of coefficients you'd be calculating. There's still quite a fair number of calculations to do, down from 100 to 55, but still quite a bit, right? So later on in this chapter, we'll learn about how to automate this process, how to automate the process of calculating all of these 55 unknowns, because surely we do not want to do that by hand, right? But for now, we'll just stick with this. And just as a last thought, this Maxwell's theorem for reciprocal displacements is basically a specific instance, a special case of a more general theorem called the Betti's law or Betti's theorem, where for any structure, if you have two systems of loads on that structure, then the Betti's theorem says that the work done, this slide really says virtual work, but it's really work done by loads PA when the load system PB is applied, is equal to the work done by PB when PA is applied. Okay, which is basically what we used here, saying that the work done by B during the application of C is equal to the work done by C during the application of B. Okay, that's what we used to show that these flexibility coefficients were the same. So anyway, this is true for any structure, a linear structure, as long as I apply, if I have a truss, beam, dam, whatever structure I have, two sets of loads, PA and PB. Work done by PA under PB is the same as work done by PB when PA is applied. So anyway, all right. So we'll stop here, and I'll see you for the quiz on Friday. Yeah, so Dr. Liu will hold office hours today from 3 to 5, and I'll hold office hours tomorrow, 3 to 5. And you can bring your questions to the office hours or post them to the discussion forum.